Drivetrain Design, Part 1 of 2. The unit objectives. The students will be able to demonstrate how applied force and friction are related. The students will be able to distinguish between static and kinetic friction. The students will be able to calculate wheel speed. The students will be able to demonstrate how to calculate a gear reduction. The students will be able to compare and contrast the different types of drivetrains along with their benefits and drawbacks. Introduction. Robots will vary greatly depending on the game challenge they are designed to play. One thing common among them is that they usually have some method for moving. The subsystem which provides the ability to move around the field is known as the drivetrain. Drivetrains may come in many different forms. The form which will be discussed in this chapter is one in which power is transmitted from a motor through some sort of gear train into a wheel which applies the force on the field surface to propel the robot forward. Friction and traction. Friction is the force that opposes motion when two surfaces rub together. There are two types of friction, static and kinetic. Static friction is the frictional force between two objects that are not moving relative to each other. It is the initial force that must be overcome to start moving. Kinetic friction is the frictional force between two surfaces that are moving relative to each other, or like sliding along each other. There are two factors which determine the maximum frictional force which can occur between two surfaces: how grippy the surfaces are, known as the coefficient of friction, and how hard the two surfaces are being pushed together, known as normal force. The maximum force of friction between two surfaces is equal to the coefficient of friction of these two surfaces multiplied by the normal force holding the two surfaces together. The maximum force of friction equals coefficient of friction times normal force. Coefficient of friction. A coefficient of friction is a constant that describes the grippiness of two surfaces sliding against each other. This is not a function of one surface, but two surfaces. Slippery objects have very low coefficients of friction, while sticky objects have very high coefficient of friction. Each pair of materials will have a coefficient of static friction and a coefficient of kinetic friction. One shouldn't confuse pure friction with actual sticky surfaces like tape or high friction coatings that bind other surfaces. These surfaces almost need to be looked as just being joined as one. Normal force. The force which presses two sliding surfaces together is referred to as normal force. This normal force is always perpendicular to the two surfaces. Often, the normal force acting on two surfaces is simply the weight of one object resting on another. In this case, the normal force is caused by gravity. Traction. Traction can be defined as the friction between a drive wheel and the surface it moves upon. It is the amount of force a wheel can apply to a surface before it slips. A wheel will have a different traction on different surfaces. When torque is applied to a wheel, it applies a force along the ground. The friction between the wheel and the ground is necessary to make it move forward. This is tractive force. Tractive force is equal to the frictional force between the wheel and the ground. If the wheel is rolling along and not slipping, it is equal to the static friction. If the applied force exceeds the maximum static friction, then the wheel will start to slip, and now the tractive force is equal to the maximum kinetic friction. Increasing traction. Since traction is dependent on the friction between the wheel and the surface, to increase traction, one must maximize this friction. The friction between two objects is dependent on the coefficient of friction between them, in this case between the wheel and the surface it drives on, and the normal force, or the weight of the robot pressing the wheel into the surface. To increase traction, one must either increase the coefficient of friction using grippier wheels, or increase the normal force acting on the wheel, a heavier robot or more weight on the drive wheels. Drivetrain terminology. The drive wheel. A wheel to which power is transferred and used to propel the robot forward. Not all wheels are drive wheels. Some wheels do not help to move the robot. Turning point. The point around which a robot is turning. Turning scrub. The friction caused by wheels dragging sideways along the ground as the robot turns. Turning scrub resists the robot turning. A zero radius turn. A zero radius turn is when a robot turns in place without moving forward. In a zero radius turn, the turning point of the robot is at the center of the robot. Chassis. The structure of a robot which holds the wheels, motors, and gear train in place. Drivetrain types. There are a number of different drivetrain types commonly found in robotics: Ackerman or car-style steering, skid steering, swerve drive, crab drive, or omnidirectional. Ackerman car-style steering. Ackerman car-style steering all the wheels move in the same direction, forward or backwards. Steering is accomplished by turning all the wheels such that all the wheels are positioned in an arc around a single point. One of the benefits of this configuration is that there is no turning scrub when it is properly set up. However, a major drawback for this type of drive is its inability to perform a zero-turn radius. Skid steer. This style is sometimes referred to as tank drive, since it is commonly used in tanks. The wheels on the right side and the left side of the drive are powered by separate motors. Steering is accomplished by varying the speed of the different sides. This type of drivetrain is capable of zero radius turns. The robot driver would simply power one side forward and the other side in reverse. This type does require two motors, but does not require a specific actuator for steering. Both motors are used when it is going straight, so all power can be used for acceleration or pushing. And there you can see an example how it's turning. This side's moving forward slower than this side, and this would be like a zero radius turn. This side's moving forward and this side's moving backwards. Swerve drive. Another type of competition robotics drivetrain is known as swerve drive. A swerve drive is one which the wheels are not only powered forwards and backwards, but also independently steered. Crab drive. A crab drive system is one which utilizes two sets of skid steer drivetrains, each pointed in a different direction. Omnidirectional drivetrain. A drivetrain that can move in any direction at a given moment without waiting for wheels to steer is called an omnidirectional drivetrain. These drivetrains use special wheels called omniwheels. Omniwheels are wheels with small rollers around the perimeter that freely spin perpendicular to the wheel's rolling direction. So each one of these wheels is moving in a different direction, which causes the overall robot to move in a diagonal direction. One problem with omnidrives is the requirement for multiple motors, with only some of the motors contributing to the robot's forward motion at most times. Drivetrain geometry and design. One of the most common types of robot drivetrain is known as skid steer drivetrain. This type of drivetrain consists of two independent sets of powered wheels, one on each side of the chassis. This drivetrain is capable of a zero radius turn if the sides are run at the same speed in opposite directions. One of the major attributes that defines a drivetrain's performance is how well it turns. There are two main properties which affect drivetrain turning: turning torque and turning scrub. Turning torque and turning scrub. Turning torque is the torque about the turning point which causes the robot to turn. Turning scrub is the friction which resists the robot turning. This is caused by wheels dragging sideways on the ground as the robot turns, resisting the motion of the turn. Designing a turning drivetrain. How does one reduce turning scrub? Turning scrub is driven by the force of friction of the wheel sliding sideways on the floor. By reducing this frictional force, one reduces turning scrub. One may also decrease the distance the wheel is from the turning point. Similarly, one could increase turning torque by increasing the frictional force or increasing the distance from the turning point. Notice that to decrease turning scrub, one must decrease the wheel friction in the left-right direction. To increase torque, one must increase the friction of the wheel in the front-back direction. It is difficult to modify the friction of a wheel in one direction without affecting the other, so it is usually best to modify the geometry of the robot chassis to help improve the robot turning. Designers should note that omnidirectional wheels have zero sideways friction. This means that a drivetrain with omni-wheel would have no turning scrub caused by that wheel. It is interesting to note that a drivetrain with two omni wheels and two traction wheels would have a turning point directly between the two traction wheels. In order to make a robot turn better, one should primarily adjust three things: the chassis geometry, wide versus narrow, long versus short, the difference in coefficient of friction between the various wheels, primarily front versus back, and the location of the robot's center of gravity. Gear train design. The gear train represents the part of the drivetrain that transmits power from the motor to the wheel. Wheel speed. The first concept to understand is how to figure out how fast the robot moves across the field based on how fast the wheel is spinning. For each time the wheel makes a full rotation, it will roll forward a distance equal to its circumference. The circumference of a wheel is equal to its diameter times pi. Once one knows the circumference of the wheel, it is possible to calculate how fast the robot is traveling based on the wheel's rotational speed. In the example below, The wheel diameter is 101.6 millimeters, or 4 inches, and is spinning at 100 revolutions per minute. So based on this, how fast is the robot traveling in millimeters per second? First, we calculate the circumference, diameter times pi. We know that the diameter is 101.6 millimeters times 3.14, which gives us a circumference of 319.024 millimeters. So the robot moves 319.024 millimeters per one wheel revolution. The wheel is moving at 100 revolutions per minute, or 100 revolutions per second. From this, one can calculate the linear ground speed of the robot. 319.024 millimeters in one revolution times 100 revolutions every 60 seconds. Our revolutions cancel out, and we multiply across the top and divide by the bottom. So we're going to multiply 319.024 times 100, then divide it by 60, and we get 531.707 millimeters per second. So the robot is moving about 532 millimeters per second, or 0.532 meters per second. Motor loading and gearing. The second concept designers must consider when designing drivetrains is how motor loading affects the gear train. It is important to consider the maximum load applied to the motor by the drivetrain. This occurs during a situation where a robot is pushing against a stationary object and is running full throttle into it. The first step in determining how many wheels are acting as a brake on the gearbox. Only wheels directly linked through gearing or chain will apply load to the gearbox and motor. The second thing to consider is to determine how much of the robot's weight is resting on each of those wheels. The traction between the wheels and the floor is dependent on the normal force pressing them together. It is important to design the gearing such that the load applied on each motor is not higher than the motor limit. Answer the following in your engineering notebook. How can you use friction to your advantage when you create your robot drivetrain? And how can you use geometry to help select the most efficient drivetrain for your robot?